So let's do a problem where we're going to Newton's second law, maybe, um, and well, anyway, energy conservation, kinematics. It sort of combines everything kind of problem. So let's say that we have a mass that starts on the top of a ramp at angle theta. The mass is mass m. It starts at a height above h equals 0. So let's call this h equals 0, and let's call this h equals ht for h top. And let's just say, ask some questions about this. And I could give you numbers, right? But as long as we can solve it in terms of the given variables, right? Don't solve it in terms of any additional variables other than the ones that you're given. Solve it in terms of the given variables. Then if I had given you the actual numbers, you could just plug it in at the end. That's not what this physics is about. Physics is about understanding how to solve the problems, not giving me a number at the end, because we can always plug in numbers. We can have a monkey plug in the numbers for us. Okay, so let's ask two questions. What's the speed of the block when it hits the spring? How far is the spring compressed? So I'm going to go ahead. I actually need to give you one additional variable in order to answer that question, and that is the height at which the spring is initially, right? This height here, or position along the ramp. We could call this position along the ramp if we want some distance, but I'll just give it a height. We'll call it hs for h, the initial height of the spring, the initial vertical height of the spring. That's going to be along the ramp. Sorry, the spring is along the ramp, but this is its vertical height before it gets compressed. Okay, so we want to give our answers to parts A and B in terms of the variables that are given. One more variable I have to give you, and that's the spring constant of the spring, the spring constant K of the spring. Okay, those are your given variables, HT, HS, M, and K, and theta. All right, so let's go ahead and solve this. Let's first solve it using Newton's second law in kinematics. So I'm going to do an AI, as in I'm going to solve it two ways, I and II. Okay, so let's try Newton's laws and kinematics. So how would we do it? Well, we can start by just writing down our kinematic equations. Let's call the x direction. The body is moving in one dimension, so we should always, if you're moving in one dimension in particular, you should always just call that dimension x. Call whatever you want, but I always just call it x. We can write down the kinematic equations. Delta x equals 1/2 a. I don't even have to write down, I'll write down subscripts. 1/2 ax squared, 1/2 a sub x t squared plus v0x times t. V sub x, the final velocity, equals the initial velocity plus acceleration in the x direction times t. Final velocity squared equals initial velocity squared plus 2a sub x delta x. Those are our three kinematic equations. And the problem-solving process is generally just identify what you know and what you don't know. Do we know what delta x is? I'm starting from the first variable. And the fact is that, well, do we know what delta x is? Delta x, for part A, what is the speed when it hits the spring? This is delta x, right? This is delta x. We really do know what delta x is, or at least, I don't know if you want to say we do know, but we can figure it out because we know that delta x, or I could have written it, shown it on the ramp here. Delta x is this distance here. And, the way I drew the h's, I didn't really, I meant to draw, h should be the height between this one and this one. So that's ht minus hs. I was just drawing in 3 dimensions and didn't quite match everything up. But anyway, this length here, this length is ht minus hs. This length here, the hypotenuse of the triangle, is delta x. So, and this angle here is theta. That's a little messy, I apologize. But delta x is given by, let me write this down. Sine theta is equal to ht minus hs divided by delta x, just looking at that triangle. Again, don't be confused by the fact that where I drew HS here, right? I really should have drawn it where at the bottom there. Okay. Hopefully that makes a little sense. Okay, so that gives me delta x. So delta x is equal to ht minus hs divided by sine theta when I solve for delta x. Okay, acceleration in the x direction. Acceleration in the x direction, we don't know yet, but we can figure out. T, the time, we don't know. Maybe we can certainly figure that out. V initial in the x direction is 0, and V final in the x direction, that's what we want to know. So that takes care of all the variables in the equations. It takes care of all the variables. So we look at what we know and what we don't know. We know delta x, we know V0x. So that means we want either this or this, the first or the third equation, because but we don't know time, we don't know acceleration. But do we know acceleration? Well, in order to find the acceleration down the ramp, you may already know the acceleration down the ramp. It's a component of g, right? It's not g as if we were dropping in free fall, but it's a component of g. But that's the Newton's second law part. We need to use Newton's second law to find the acceleration down the ramp. Let's do a little aside and do Newton's second law. N2 to find acceleration. So how do we apply Newton's second law? So Newton's second law, we draw a free body diagram. Let's draw the mass m, and what goes into a free body diagram? What goes in a free body diagram are all the forces on the individual mass that we have taken out of the original picture. So let's think about the forces on this mass as it travels down the ramp. Well, one of the things about Newton's second law is you always have to say, well, how do I know what the forces are? Well, there are only certain forces that they could be. It could be a normal force. It could be in contact with a surface. There could be a weight, as long as it's on a planet or something like a planet. There could be a spring. There could be a rope attached, tension. There could be a frictional force, F sub friction. And there could be some other force, like a hand pushing it, that you don't know what to call it, although a hand would really just be a normal force. So maybe you'd say some other applied force. But you just got to look at what's touching it and say, okay, so what is there? Well, for this mass, there is indeed a normal force that is perpendicular to the surface. There's a gravitational force, which is straight down towards the surface of the Earth. There is no spring attached, not at the top. There's no spring attached. And we're just talking about the motion before it ever hits the spring. There's no rope attached, so there's no tension. And I didn't say there was friction, so you should assume no friction unless you're otherwise told. So this is a complete free body diagram of the mass. And then what you want to do is choose your axes, choose your coordinate axes, which we essentially already said. Plus x should be down the ramp. Therefore, plus y should be perpendicular to the ramp. And then Newton's second law, you apply Newton's second law in the x direction. F net, the components of the net force in the x direction, equals the mass times the acceleration in the x direction. And the component of the net force in the y direction equals the mass times the acceleration in the y direction. So you write down Newton's second law, you have your free body diagram, and then the next step is to identify the left-hand side of this equation from your free body diagram, and then identify if we know anything on the right-hand side of the equation. So this is the process, is that we want to now just say, hey, okay, let's start with this one, the net force in the x direction from the free body diagram. Does the normal force have an x component? No. Does mg have an x component? Yes, mg has an x component. That's this. This is mg's y component. And you can do the trigonometry to figure out if that's theta. That I guess it doesn't matter if I keep drawing in red. That the net force in the x direction, excuse me, is mg times sine of theta. That's the net force in the x direction, and that equals m a sub x. We don't know any, well, we're given m on the right, And actually a sub x is what we were looking for. So from this equation, we get a sub x equals g sine theta. So that gives us the acceleration we were looking for on the other page. Let's just go one step further and do f net y. In the y direction, you've got the normal force pointing upwards, and you've got the y component of mg pointing downwards, so you have to explicitly put in the minus sign. You got to pay attention to the fact that the plus y-axis is pointing up, and mgy is pointing down, and you need to put in the minus sign explicitly. All these constants that we're drawing are positive constants. So this is going to be mg, and you can figure out from looking at doing the trigonometry of the problem, it's going to be mg cosine theta equals ma sub y. And again, if we were just solving Newton's second law problem here, we say, okay, now we have plugged in the forces from the free body diagram on the left-hand side of the equation. What do we know about the right-hand side of the equation? This body is not moving perpendicular to the ramp in the y direction, so that's equal to 0. So what does this tell us? This tells us that the normal force is equal to mg cosine theta. It just tells us the size of the normal force. Okay, but you didn't need to know that. What you did need to know is the acceleration is g sine theta. So we can go back here and we can say, okay, now we know the acceleration is g sine theta. And now we know enough information to answer the question, part A. And so since we found A and delta x, the equation we should use is the third one. Let's go ahead and just plug into the third equation. What we're looking for is vx squared, v0x is 0, plus 2a is g sine theta. Delta x is ht minus hs over sine theta. And lo and behold, the sine thetas cancel, and we get, therefore, v sub x equals the square root of 2g times the change in height, ht minus hs, which maybe, if you remember back, should look sort of familiar. That comes up a lot, the fact that when you drop something through a height, even if it's sliding down a ramp or if it's in free fall, the velocity at the bottom is still 2g times the change in height. Okay, that's the answer to part A from a kinematics and Newton's second law point of view.